This is a video on derivatives of the exponential function e to the x. And when we take derivatives, a lot of them are all based off of the limit of the difference quotient for the function. We're not going to show why this is true, but that's where this comes from. But if I said for derivatives of f of x equals e to the x, if I said given f of x equals e to the x, remember e is our natural base, e to the x, the derivative of that actually, f prime of x, is equal to itself. So it's one of the easier rules to memorize because the derivative of e to the x is just e to the x. So we'll use that in a few examples here, just so you can see where it might show up, and then we'll talk about some special cases. So if I said to differentiate, remember that means take the derivative of, let's look at this first one here. We'll say we have y equals e to the x plus 7x squared minus 9. So when you're going to take the derivative here, you first should see if there's anything you need to rewrite. If you didn't have x to a power and you had roots in there, x is in the denominator, you'd want to probably rewrite this. But each of these terms is okay to be differentiated right now. So taking a look at the derivative here, we have y prime equals, well, the derivative of e to the x is e to the x, right? So we're doing this term by term, plus the derivative of 7x squared. Well, the 2 comes down, 2 times 7 makes us plus 14, x to the power becomes 1, and then the derivative of negative 9 as a constant goes to 0. So we have y prime equals e to the x plus 14x. So similar to the rules you've seen before, it's really not different at all. Let's take a look at another one here. If I said we have y equals 12 e to the x plus 7 over x squared. When you look at this one, first off, you should notice that, right, 12 times e to the x, it's a constant times a function. That's okay, don't let that throw you off, right? It's just having a coefficient in front. The 7 over x squared, though, we want to rewrite that so we can have x to a power, so we can use our power rule. So the first thing you want to do is rewrite this. And when I rewrite this, I end up with y equals, this is 12 e to the x plus 7. Now x squared, to move it to the numerator, becomes x to the negative 2 power, remember, right? You make the power negative to move it up. Notice I didn't take the derivative at all yet. I'm just rewriting the original function. Don't start taking parts of this as a derivative. You want to just rewrite the function, then take the derivative in its entirety. So now I'll take y prime, and I'll label it y prime. And the derivative of 12 e to the x, well, constant times a function, the constant stays in front, and then you take the derivative of the function. The derivative of e to the x, well, we just learned that is e to the x, so it's 12 e to the x, plus here we got 7x to the negative 2. Well, the negative 2, remember, comes down in front by our power rule. Negative 2 times 7 make this negative 14. X to the power gets reduced by 1. Negative 2 minus 1 is negative 3. And then let's simplify this. We have y prime equals 12 e to the x positive times a negative makes negative. If you wrote negative right away here, that would have been okay. Negative 14. X to the negative 3, the negative exponent tells you to move that to the denominator as x to the positive 3. Remember, the exponent's only acting on the x, not on the 14. And then we have it. The next example will combine a couple other rules. Let's take a look at y equals x cubed times e to the x. All right, so x cubed e to the x, well, when you look at this, you should notice that you have a function times a function, right? X cubed times e to the x. So this is a product rule. You can't just take the derivative of each piece individually. You have to use a product rule here because you have a function times a function. So if you have a function times a function, we follow the product rule. So y prime, remember how the product rule works. I'm going to take the derivative of the first function. So the derivative of x cubed, which is 3x squared, times, you leave the second alone, so times e to the x, plus you take the derivative of the second function, which in this case is just derivative of e to the x is e to the x, right? So I took the derivative there, times the original first, so times x cubed. And, you know, really you could leave it like this, and we'll simplify it just so you can see it. We have y prime equals 3x squared e to the x plus x cubed e to the x. And if you leave it like that, that's okay. You may also see this later on where, you know, we're trying to solve for something. We might factor out from here at a greatest common factor. The 3x squared e to the x and the x cubed e to the x, well, they have an x squared as a common factor, and they also have e to the x as a common factor. So if I factor that out, from the first term, I'm just going to be left with 3 plus the second term, factoring out the x squared e to the x, I'm just left with x. So we have x squared e to the x times 3 plus x. If you left in the previous step, that would have been fine. It doesn't change anything. But later on, you will want to know how to factor this. So it's good to get in the practice of just understanding where that simplification comes from. And then we'll look at this here. If I said y equals e to the x over x to the 4th power. For this one, you should notice that you have a function divided by a function. And for a function divided by a function, you want to use quotient rule. Now, you might notice that you could rewrite this right away and move the x to the 4th up to the numerator as x to the negative 4 times e to the x. If you did that, it would be a product rule question. But because I want to demonstrate the quotient rule and remember how to use it, I'll do this as, you know, we have division of functions, so we're going to use quotient rule. And remember how that works. You want the derivative of the numerator, so the derivative of e to the x is e to the x times the denominator, so times x to the 4th stays the same, minus the derivative of the denominator, which is 4x cubed, times the numerator, so times e to the x, and this is all over the denominator squared, so x to the 4th squared. And we'll simplify this. If we simplify this, we have y prime equals. Now, up here, you should notice that, you know, I can factor out, just kind of like how I did in the last problem. These have an e to the x in common. They also have an x to the 3rd power. So I'm going to take out a GCF of x to the 3rd e to the x. And what's left inside here, e to the x times x to the 4th. If I factor out the x to the 3rd e to the x, I'm just left with x for my first term. Minus here, I'm factoring out the x to the 3rd e to the x. I'm just left with minus 4. And this is all over x to the 4th squared. When you have a power to a power, remember you multiply. So this will be x to the 8th. And now if I can simplify this, I should. If I have this factor of x to the 3rd and this factor of x to the 8th here, right, one numerator, one denominator, I can cancel 3 of these with 3 of these, and I'm left with x to the 5th in the denominator. So my derivative for y prime is equal to e to the x times x minus 4 all over x to the 5th. And we can leave it in that form. That's a 4 there. Alright, so those were, you know, problems that involve derivatives of just e to the x. The next thing we'll talk about is what if, you know, when we have e to the x here, instead of this being e to the x, it's e to some other functional power. So it's really a variation of chain rule. This is chain rule for exponentials. And we'll talk about it here. So this is the chain rule for y equals e to the f of x power is how I'll write it. So chain rule had to do with if we had a function inside of a function, a composition of functions. When I have y equals e to the f of x, like I wrote here, right, we have a function f of x, which is inside of the e function, right? It's replacing where the x was. So I'll write this out as given y equals e to the f of x power. So the power is a function. Then y prime, right, the derivative is equal to, using chain rule, if you remember how chain rule works, it says, you take the derivative of the outside function, keeping the inside the same. Well, the derivative of the outside is e, and then you keep the inside the same to the f of x, right? Derivative of e to the x is e to the x, so the derivative of e to the f of x would be e to the f of x times the derivative of the inside function, which is the exponent here, so times f prime of x. So the derivative here, right, you really take the derivative of the outside is just you keep e to the f of x times the derivative of the inside, which is f prime of x. Kind of a little shortcut thing I say to help you understand a little easier is for derivatives of e, you keep what you see and then you multiply by the derivative of the exponent. All right, so for derivatives of e, you keep what you see to multiply by derivatives of the exponent. It's chain rule though, right? It's the chain rule for e to some function that's a power. E is the outside function, whatever's in the exponent is the inside function. So if we were to do some examples here. And I'll say differentiate. First one I'll look at is y equals e to the 4x. So y prime, we have e to a power, it's a function. So derivatives of e, you keep what you see, right? So e to the 4x, that's your outside, times the derivative of the inside. Well, derivative of the exponent is derivative of 4x is times 4. So y prime just equals 4 e to the 4x. Alright, so for derivatives of e, you keep what you see and you multiply by the derivative of the exponent. How about this here? We have y equals e to the 3x squared plus 7x. And you may want to pause this and try this on your own. We have a derivative of e to a power, it's a function. So the derivative here, remember what we said, it's a chain rule for e. So derivative of the outside, derivative of e to the x, normal e to the x, we just keep this as e to the 3x squared plus 7x, times the derivative of the exponent, well the exponent in this case, 3x squared plus 7x, taking the derivative of that function, derivative of 3x squared is 6x, plus derivative of 7x is just plus 7. Make sure you put parentheses around this, right, because it's times that whole exponent. So derivative of e, you keep what you see, multiply by the derivative of the exponent, and then this really can't be simplified too much more. If you wanted to distribute this through here, you could. I mean, I really wouldn't. It's not going to be beneficial in the long run. So I would leave this as you have 6x plus 7 times e to the 3x squared plus 7x, and you could leave it in that form. Let's take a look at a couple others here. If I said I had f of x equals e to the square root of 2x plus 3 power. So in looking at this one, the first thing I want to do is rewrite this. Because if you have a radical in there, we want to write that as an exponent, remember. So to rewrite this, I'm going to really rewrite f of x. I'm not taking any derivative yet, right? This is still the same original function, just rewritten in an equivalent form. We're going to have e to the power of 2x plus 3, when you take the square root, is 2x plus 3 to the, remember, square root, this is going to be 1 over the index of the root, which is 2, so the 1/2 power. And now we're ready to take the derivative. So if I go to take f prime of x, remember how it works, chain rule on e. So derivative of e, you keep what you see, because derivative of e to the x will be e to the x, so we're going to keep e to the 2x plus 3 to the 1/2 times the derivative of the exponent. Well, the derivative of the exponent here actually is going to be a chain rule in itself, because you have a function inside of a function. So how does that work? Well, the 1/2 will come down in front, so you would have 1/2 times 2x plus 3, and then subtract 1 from the exponent would be negative 1/2, times the derivative of the inside, right? This is chain rule, so times 2. So this is the first part. right? This is derivative of e. You keep what you see because you keep, this is the chain rule for e. Take the derivative of the exponent is right here. We had to use chain rule on this. Bring the 1/2 down, keep the inside, subtract 1 from the exponent, and then times the derivative of the inside of that, which is 2. And so it's a little tricky because the chain rule within a chain rule. And now we'll simplify. So taking a look at this, these 2's are going to cancel, which is kind of nice. You end up with f prime of x equals, right, because it's 2 times a half, so just cancel to a 1. E to the 2x plus 3 to the 1/2. I could really write that as the square root of 2x plus 3 again. Over, because the negative exponent moves it to the denominator, this will be 2x plus 3. And then the 1/2 power on this tells you it's the square root in the denominator. So the derivative here, all right, we have e to the square root of 2x plus 3 over the square root of 2x plus 3. So we use the chain rule twice just to kind of go over this again because it's a little complicated. We had e to a functional power, so you keep the first part when you take the chain rule, derivative of the first, or derivative of the outside. Derivative of the outside is just itself, keep the inside the same, times the derivative of the inside function. This is the inside function, so you keep the first part as e to the 2x plus 3 to the 1/2 times the derivative of the inside, bring the 1/2 down, leave the inside the same, subtract 1 from the exponent, times the derivative of the inside. It's the chain rule when you take the derivative of the exponent there. So it's a chain rule within the chain rule. Let's take a look at another one. If I said I had y equals the square root of e to the x plus 1. Again, the first thing you should notice here is that we're going to rewrite this. So I'm going to rewrite this as y equals e to the x plus 1 to the 1/2 power. Because remember, any roots you see you want to write as exponents, as rational exponents. So square root, right, that's 1 over 2. And now I want to take the derivative for y prime. Now in this case, when you take the derivative, right, you have this function raised to a power. This is going to be chain rule. So chain rule as we traditionally would use it. We're going to bring the 1/2 down. Keep the inside the same, right? The way chain rule works is, you know, take the derivative of the outside, keep the inside the same. Then we're going to subtract 1 from this exponent, right? So you bring the 1/2 down, keep the inside the same, subtract 1 from the exponent, makes it negative 1/2, times the derivative of the inside. Well, the derivative of the inside of this, derivative of e to the x is just e to the x, derivative of 1 is 0, so just times e to the x. And then that's the derivative. If I asked you not to simplify, if I said take the derivative and do not simplify, you'd leave it alone. Here, this does simplify. We end up with y prime equals, this negative exponent will tell you moves to the denominator, e to the x, so that's in the numerator. So it's e to the x times 1 in the numerator, which is e to the x. In my denominator, I'll have 2, and then this negative exponent tells you move it down, e to the x plus 1 raised to the 1/2. 1/2 power is the square root, so it's the square root of e to the x plus 1 down here. Just rewriting it using the radical. Alright, let's take a look at another one here. Do this on a new page. We'll call this letter E. Refocus that. So if we had y equals there we go. If we had y equals e to the x plus x to the third power minus xe to the 2x. Remember, we're trying to take the derivative. We're trying to differentiate this. we do it term by term. All right, I don't see any problems in terms of having any square roots or any variables in the denominator. So let's take a look at what happens for y prime. So derivative of e to the x, well, derivative of e to the x is just e to the x, plus the derivative of x cubed is plus 3x squared, bringing the power down using the power rule, subtract 1 from the exponent, minus, now I have x e to the 2x. The key thing here is that you have to notice you have a product here. It's a function times a function. So that last term you have to use the product rule on. Don't forget about that. Using the product rule here, remember how it works. This minus sign though belongs to everything, so I'm going to do it in parentheses after it. Product rule says you take the derivative of the first function, so derivative of x would just be 1 times, you leave the second alone, so times e to the 2x, plus the derivative of the second function. Well, derivative of e to the 2x, that's a chain rule on e, because you have e to a function. So derivatives of e, you keep what you see, so we keep e to the 2x times the derivative of the inside. The inside is just the derivative of the exponent, so times 2. And then you multiply by the original first function, right? This is the product rule. If you need a little bit of help seeing it, right, when we did product rule, we called this f and this g. And then when we looked at this, you know, the first part of the product rule would be f prime times g plus g prime times f. Just following our product rule that we learned earlier. So that's how product rule works. Let's simplify this down here. So we're going to bring this negative sign through here. So we have y prime equals, we have e to the x plus 3x squared. Distributing a negative into here, negative 1 times 1 times e to the 2x is going to be just negative e to the 2x. And then this negative here, remember, gets distributed through, and negative times a positive here makes this a negative, and then 2 times x e to the 2x, I'll write as 2x e to the 2x. Traditionally, we typically put you know, those coefficients in front of the e to the 2x. And are any of these like terms? Well, no. These aren't like terms because this has an x and this doesn't. These aren't like terms because, you know, the exponents on the e are different. So you leave it. There's nothing else to do with this. This is the function for the derivative. Keeping in mind though, watch out for these product rules. Sometimes people just try to take the derivative of each piece and put them next to each other, and that's not what you do, right? You have to follow the product rule when you have a function times a function. And that's what we did here. Within that product rule, we had a chain rule on e. For derivatives of e, you keep what you see and then multiply by the derivative of the exponent. Just to kind of show this, this is actually easier than what we've already talked about. If I said y equals e to the x, now I've already said the derivative of this is y equals e to the x. If I didn't recognize that though, and I tried to do a chain rule on it for y prime, remember derivatives of e, you keep what you see. So the derivative of the, you know, the outside function e to the x, you keep e to the x times the derivative of the exponent. What's the derivative of the exponent? Well, derivative of x is just times 1. So it'll just be e to the x, and that's how you get y prime equals e to the x. I wouldn't expect you to show this. You should just know that derivative. But just so you see where, you know, it kind of comes out equal in case you forget about it. Sometimes people do. You know, the chain rule will always just give you back what you needed originally if it wasn't necessarily to apply it. And let's just take a look at one more example here. We'll do an applied example. So we'll say Justin purchases a video security system valued by this function v of t equals 17,500 e to the negative 0.0834 t, where v of t is the value in dollars T years after it is purchased. Alright, so they're giving us this function v of t. And the first question we'll ask is estimate the value of the system T years. I'm sorry, 5 years. So estimate the value of the system 5 years after it was purchased. So for this first part, all they're really asking you to do is find the value at 5 years. We don't have to do anything here. The function is already set up the way we need it. We just have to find v of 5. To find v of 5, we're going to have 17,500 e to the negative 0.0834 times 5 power. And I'll do this on the calculator here. So if we do that, we have 17,500 times second e to the, now make sure you put, both things are being multiplied in the parentheses on e here, so the negative 0.0834 times 5, close the parenthesis and then hit enter. If your calculator does not display everything on the screen, you want to multiply these together first, then hit the e button and then multiply by 17,500, so you kind of work backwards from the exponent. So this gives us, we got 11,532.8661. Remember, this is money, so we're going to round to 2 decimal places, so 0.87. So we have this as $11,532.87. So after 5 years, the value of the security system will be $11,532.87. Something to notice is that what's the original value of the system, in case that came up and we asked you about it. Well, that's when t equals 0, right? So when t equals 0, this would be e to the 0 power, which is just 1. So the value, this is the initial amount, that's 17,500. It's similar to like your principal when you have a simple interest type problem, right? So 17,500 would be how much the system was when it was brand new. Right, so after 5 years, it's depreciated to $11,532.87. The second part of the question will say, what is the rate of change in value of the system at the end of 5 years. So this is a different question. When you say rate of change, if we're saying what is the rate of change in the value of the system? Well, rate of change, tells you take the derivative. So first thing you want to do is take the derivative. Then you want to substitute in the 5 years. Don't put the 5 years and try to take the derivative of this. This is a constant, so that would just give you 0. So you want to find v prime of t first. Then you want to go through and actually evaluate it at 5. So v prime of t, well, the original function, up here, 17,500 e to the negative 0.0834 t, how do you take the derivative of this? Well, constant in front will stay a constant in front, 17,500. And then derivatives of e, remember, when you have e to a power that's a function, derivatives of e, use the chain rule on that. You keep what you see, because e to the x is just e to the x. So derivative of the outside, e to the negative 0.0834 t. So derivatives of e, you keep what you see. times the derivative of the exponent. The derivative of negative 0.0834t is just times negative 0.0834. And that's our derivative. If you wanted to simplify it, you could multiply those coefficients together. And you could say we have 17,500. All right, so 17,500 times negative 0.0834 gives us negative 1459.5, and then this is e to the negative 0.0834 t power. Now once I have that, right, that's the derivative, that's the rate of change at any time t. We want to find v prime of 5, because we wanted to know at the end of 5 years what the rate of change was. Well, then we're subbing 5 into this, right? So this would be negative 1459.5 e to the negative 0.0834 times 5. And again, we'll substitute this in on the calculator. If your calculator does not show everything on the screen, remember, multiply these exponents together, right? So multiply that together, then hit the E button, then multiply by the coefficient, right? So start in the exponent and work your way backwards. If it displays everything on the screen like this calculator that I have here, then you can just type it in as you see it. Negative 1459.5 times second function e to the negative 0.0834 times 5. Make sure you have that all in parentheses. And then once you have that, hit enter. And I've got negative $961.84. So it's negative 961.84. Now remember, we're talking dollars here, right? So I rounded to 2 decimal places because it's dollars. Remember, this is not just straight dollars though. This is the derivative. So the units on this are the units of v, which are dollars, or units of y, if you want to think of it that way, over units of x, or units of v versus units of t. So it's dollars per year, because t was in years. So negative $961.84 per year. And that's the rate of change, but let's talk about what that means, right? If I'm talking about this in terms of what it means, that's telling us the negative, that the rate of change, right? That negative tells you it's decreasing. So the value of the system is decreasing at a rate of what we see here, $961.84 per year at the end of 5 years. So, you know, it's important to understand what you found. You know, that interpretation sentence really does make a difference. So it's decreasing at a rate of $961.84 per year at the end of 5 years. Now remember, that's at the instant that we're at the end of 5 years. So it's not going to be, it's not a constant rate of change. You know, if I had it at the end of 4 years, we get a different value. But at that point in time, that's how much the system is depreciating by per year. All right, so hopefully this helped with derivatives of e to a power. Remember, for derivatives of e, you keep what you see, and then you multiply by the derivative of the exponent. That's really the key thing there. It's a chain rule on e. It's kind of a shorthand kind of way of remembering what to do with it.